I'm going to go ahead and start recording. So section 5.5 is applications of exponential functions. Everybody can see my screen right now?
Yep.
Okay.
Yeah. Yep.
I just want to make sure I was sharing the correct screen. So there's two main applications that are given here, exponential growth and exponential decay. And you don't need to know this, but these equations that are given here are technically differential equations. So if you ever got interested in those sorts of things, that's where that comes from. And the solutions are these two. And you see that they're the exact same thing, just with one having a positive k and the other having a negative. And that's nothing more than the indicator of growth, right? Positive, and decay, negative. So you might know where this is going. Almost every time you see growth and decay, eventually you have to do a carbon dating problem. But at least it's something interesting. It's something that's actually used. As opposed to, I think, a problem in here, something about widgets. All right. So let's look at this first example. Suppose that a population of rabbits grows exponentially. That is, that the rate of population growth depends on the size of the population. Further, suppose that on Monday at 8, there's 100 of them. And at that same time on Wednesday, there's now 130. So find an exponential function that represents the rabbit population at time t, where t is measured in days from Monday at 8. So we're given 2 points here. We're given that at time 0, right, Monday at 8, because time is measured days from then, that there are 100 rabbits. And then we're also given that on Wednesday at 8 a.m., which would be 2 days from Monday at 8, there are now 130 rabbits. Now, this is a growth problem. So our equation that we start with should be this guy. So we've got y equals ce to the kt. So then we can substitute these values in. So 100 is equal to ce to the k times 0. And the other one is 130 equals ce to the k times 2. We can start back here because k times 0 is obviously 0. And we should know that e to the 0 is 1. That's one of those properties of the exponential that we had. So this gives us 100 equals c. That's one of the constants we had to solve for. The other is k, which is that constant of proportionality. So we can come over here now and we can substitute c. Divide by 100 on both sides. We can easily drop a 0 there. And then obviously these are gone. So we have e to the 2k is now equal to 13/10. To get rid of e, we need to take the natural log of both sides. So these are gone. And finally, to get k, we just need to divide by 2 or multiply by a half, same thing. And I've done this already. This is approximately 0.1312. And I'll send out these notes to you as soon as I get done today, because I don't believe I put these up yet.
And where are you putting the notes at?
Where am I putting them?
Yeah.
Under the guided notes tab.
Okay.
On Blackboard, it says Chapter 5 worked out notes.
Okay, thank you.
Mm-hmm. All right, so we have C and we have K, which means we can write the equation for any time t. So this is 100 e to the 0.1312 t. That was our goal, was to get the equation. So any questions about that guy?
Nope.
All right. And it says, find the time that the population will be 200 rabbits. And notice it says double the original. So we're going to do 200 equals 100 e to the 0.1312 t. Another way that you could approach this is when it says double the original, you could just start immediately with 2 equals the exponential. Because notice if I divide both sides here by 100, I get back 2. That's why they said double the original. If it said, 8 times the original, then you would just set this to 8. Get rid of the e by taking log. Those are gone. And if I want to be precise, instead of dividing by 0.1312, I'm going to go back. I have this equation right here for k. I'm going to divide by that whole thing. Just because I want to be as accurate as possible. So we've got, we calculate that. Looks like it comes out as 5.28. Now it says find the time. Time was measured in days. So it appears it has to be over 5 days. So 5.28 days. All right. So not a whole lot of calculus going on here so far. We're really just plugging in and doing some manipulation. All right. Suppose that 2,000 is invested in an account that earns 8% compounded continuously. What will be the balance in 1 year? So recall that for compounded continuously, we had this equation, which in fact looks just like a growth equation. So it says 2,000 is invested. So that's the principal amounts, right? The initial value that we put in. I think actually I use A for this. So let's just plug those in. So we have that A is equal to 2,000. E, now it says 8%. That's 0.08. And then 1 year. So we'll assume time is in years. And that comes out as this value. Second part says, when will the original investment be tripled? So again, that really means when will A equal 6,000? Or when does 3 equal the exponential? So you could have set it up like this. And divide it by 2,000. And still gotten to that. So I'm just going to do this. I take log. So t is equal to natural log 3 over 0.08. Looks like 13.73. And that would be years. So quite a long time to get 3 times the amount. So let me just look through here real quick. I think maybe I will stop. There's quite a bit left. I think I'll stop after these next 2 problems. I think that should be enough. Suppose that the decay of a particular radioactive isotope is described by the equation given here, where Y is the amount of the isotope in grams and T is time in years. Find the half-life. So again, half-life means if we started with 200, we got to get down to 100. And this is a very common problem that you'll see. So common that I have memorized the natural log of 1/2. Ahead of myself here. That is going to yield 13.86. That quantity is years. Takes about 13.86 years for half of that isotope to decay. So as I said, eventually we're going to get to carbon dating. So here it is. Radioactive substance, carbon-14, is known to maintain a constant level in living plants and animals. When a plant or animal dies, the decay is, or the level of decay is proportional to the amount present. And so it says that means it really just decays exponentially. And the constant of proportionality, K, is given here. So we're given an animal bone. They found it, they dug it up, and it contains 40% of its original amount. So how old is the bone? Now, this is a decay, which means my equation has to be negative KT. And I'm going to plug K in at the very end because I don't feel like writing all 6 decimal places each step of the way. Now it says that there's 40% of its original. So if C is the original amount, Y is equal to 40% of that. So 40% being 0.4. So this is 0.4 C equals CE to the minus KT. If I divide through by C, it cancels everywhere. And you see that we get 0.4 is equal to the exponential. So I keep telling you that that would happen. So that's what we got. To get rid of the E, we got to take natural log. That then makes those cancel. And we have that the natural log of 0.4 is equal to minus KT. We're looking for how old it is, so we need to solve for T. So T is natural log of 0.4 divided by negative K. And if I plug that in, negative 30124. So let me give you a number for that. It appears, oops, put 4, not 0.4. That'll severely dampen things. So T is equal to 7,389.44. So that bone's pretty old, but not as old as you might think. Anybody know what era that is?
No.
I'm just curious now if that falls into. I guess that would have to be a mammal of some sort. You guys are probably thinking I'm crazy. All right. Let's see. Do I want to start this problem? Sure, let's go ahead and do this one. It won't take long. We just got to plug a number in, and then we got to take a derivative. So I'll do this one, then I'll cut you loose. All right. So we're talking about limited growth. I thought there was a graph here, but I guess not. So when we're talking about limited growth, we're looking at something that's increasing and then kind of levels off. And it says here, as t increases, y approaches c. So there's some constant out front here. So whatever this this dashed line is, it would have to be c. And you see this kind of stuff a lot in like basic currents in electricity. You know, your current builds up exponentially, but then levels off to some value. And then you see the reverse when you're talking about like capacitors and decharging them. All right, so here's what I was talking about earlier, right? We got a man making widgets, which is the definition of some made up object. He says he can make this amount per week after T weeks. So how many widgets will this man produce during his 4th week? Well, we just plug 4 in. So if I do that quickly, it's like 30.12. And if I had to say how many did he make, well, I guess that means he made 31. Then it says, at what rate will his widget making skills be improving at the end of the 4th week and the 10th week? Keyword here being rate. So whenever we see that, we should know we are taking a derivative. So my equation was 100 E, or sorry, 1 minus E 0.3T. Okay. So derivative of that. So dn dt. So I'm going to get the derivative of the exponential. The 100 stays out in front. Derivative of exponential is, now it's already a minus sign there, but then when I bring down that negative 0.3, it's going to turn it positive. And then I still have the exponential. So that's going to be what, 30 e to the minus 0.3t? Make sure I'm not going crazy. Nope, 30. All right. Now it says 4th week and then 10th week. So we just want to know what's the derivative when t is equal to 4. So that's 30 e to the minus 0.3 times 4. 30. Plug it in. That comes out to be about 9.03. And finally, dn dt of t equal 10 is 30e to the minus 0.3 times 10. And that's about 0.49. So because it's leveling off, right, he's going to be producing about the same amount after 10 weeks. He's only going to be producing about 1 to 2 more at that point per week.
I have a question.
Yep, go ahead.
For the answer for A for that, how did you get that 30.12? Because I keep getting 69.88.
Let me check. I may have forgotten to do the 1 minus part. Yeah, I forgot to do 1 minus. Thank you.
Welcome.
There we go. Anything else, guys?
Nope.
All right, I'm going to go ahead and stop recording.